Well, good morning, everybody. How are we doing this morning? Yeah, I'm still jet lagged from daylight savings time. I always feel ripped off because I have jet lag, but I didn't do anything fun. Right? So, always a problem. This is part of our ultra-fast blitz of the first part of optics. I don't know if you noticed, but last Tuesday, we did one chapter, right, in one day. We're going to do the same thing today. I'm going to do all chapter 25 today. And then we're actually going to spend some time in chapter 26. It's kind of the big meaty chapter. Lots of stuff going on there. Monday. Our lab on Monday is lecture. We're going to have I just needed some additional time in chapter 26. So like next week, pretty much, Monday, Tuesday, Thursday is going to be chapter 26. It's not like, I don't want you to panic. It's not like super difficult. It's just there's a lot going on in the chapter with refraction and lenses. And I do take a little bit more time in the 2 series to talk more about the biology of the eye and how to do corrective optics with eyeglasses and stuff like that. We're gonna spend some time with some of the lens stuff. So just keeping you aware of what's happening as far as the pacing goes, right? Today we're going to talk about, how we apply all of Maxwell's equations and all this wave theory that Maxwell developed along with others to mirrors, and then next week it will be lenses. One of the things that makes optics a little bit simpler is the fact that we're going to sidestep sort of the whole issue, is light a wave or is it a particle? It's still a wave, and what we're doing is wave mechanics. But instead of having to get into the nitty-gritties of all these wiggles everywhere, we are going to model light as rays. The ray model, and you'll see me drawing some of these rays today. We're going to do some computer simulations with the rays. And if you've ever heard of ray tracing, this is the very beginnings of it. Light and or sound, but in this case light, we're going to assume is being emitted from a source, a point source. It's not spread out, it's contained. And as it emits, you get the light is wiggling everywhere, right? It's coming out in all directions. And typically we're going to be concerned with one of those directions, right? I mean, we don't really care that the light hits the ceiling. We're more like, we want to look at the light as it comes down and strikes whatever we're trying to illuminate. So instead of trying to think of all these wiggles, we're just going to draw a line, okay, with an arrow on it. Please don't panic. This is not a vector, okay? It's simply an arrow, okay, that is pointing in the directions that the waves are traveling, right? If you want to think of it as when the electric fields are going up and down and the magnetic fields are at 90 degrees and the wave is propagating perpendicular to that, we're drawing that ray. Technically it could be a vector, but we're going to leave it as a ray. It's going to be a line. We're going to assume correctly, because this is what happens, light travels in straight lines, right? It doesn't get deviated or bounced unless it runs into something else, right? And we will start talking about those reflections. But for us, in the next 2.5 weeks, light is a wave, and we're not going to be drawing any of those waves. We're just going to be drawing arrows for where those waves are headed. So that brings us to mirrors, okay, and how mirrors work and how they function. We're going to talk about 2 types of mirrors today. The mirror you are familiar with, the one that hangs in your bathroom or your house or wherever, right? And then we're going to get into more specialized mirrors called spherical mirrors, which you are also familiar with, and we'll talk about that later, okay? But the first question I have for you, I brought here a flat plane mirror, okay? Plane as in not airplane, right? But like flat, right? Okay. It's nice and flat, right? And there's a rule, okay, for how light is going to interact with this surface. It's called the law of reflection. Angle in equals angle out. But I need you to notice something in this diagram on the screen. Where are those angles measured from? From the normal, from the perpendicular to the surface. In optics, our angles, when it comes to reflection and refraction, are always referenced to the normal to the surface of impact. This is, you may or may not catch it later, but it makes the math a little bit easier. But physicists, I'm not going to lump myself into this category. Physics textbook authors have decided that that's, too easy, and they'll try to do some kind of tricky things to throw you off the scent, for example. Okay? They'll say, and usually, this is a three-dimensional drawing of it, right? But usually we'll draw like a ray diagram, and we'll have a beam of light come in and strike the surface and bounce off, right? Something like that. And they'll say something, they'll say like a pond or a lake surface, right, is perfectly still in the morning. And the sun is at an angle of 20 degrees above the horizon, right? What are they doing? Did they give you the correct angle? No, you got to subtract. So that right there is that's a textbook issue. Okay, right? They're just trying to make it harder because apparently optics needs to be harder or something like that. I don't understand. So just make sure when you're given an angle in a problem that you understand where that angle is being measured from. The reference angle in optics is always measured from the perpendicular to the surface, from the normal to the surface. And so in this particular thing, right, if this angle right here is 70 degrees, right, if the light makes an angle of 7 degrees from the normal to the surface, then what's this angle over here? 70 degrees, right? So for a plane mirror, a flat mirror, right, angle in equals angle out. This actually holds true for curved mirrors, but curved mirrors have different planes in them at every radius, right? You can see here that they're using theta I in this diagram and theta R, incident and reflected. So this is just some terminology, right? The light's coming in and then bounces off the reflective surface. So it comes in as an incident ray. It's incident to the material, and then it reflects off. Unfortunately, this R is going to get screwed up in next chapter because we have to talk about refraction. So we're just going to have to come up with a better way to start keeping track of those kinds of things. But let's talk about this reflection right here. Okay, there's lots of stuff going on. We need to define some terminology, but I think we need to get something out of the way right now. Okay. Which way does this mirror flip images? You've looked in a mirror before, right? Okay. So when you're standing there looking at yourself in the mirror, right, and you bring up your right hand, what happens in the mirror? The left hand goes up. Your evil twin in the mirror, right? Yeah, okay. So there seems to be a flipping there, right? Right for left, that sort of thing. Okay. So there's only 3 axes that we can flip along. And we can do more than one of these, right? But there are 3 types of reflections that can occur, okay? Or not so much in reflections. All reflections are just angle in equals angle out. But there are 3 orientations that reflection is going to take, okay? And those are a right-left reversal, a top-bottom reversal. We try to avoid up-down. We do top-bottom instead, okay? And what would be the third one? In and out. We call that front to back in optics, okay? So left-right, top-bottom, front to back. Those are the different sort of orientations that we have in optics, okay? So my question for you is, which one of the reversals is happening in a plane mirror? Left, right, top, bottom, or front to back? Left, right? Okay. So how do we determine what's true? No, we do an experiment, right? Okay, we do an experiment. We can do this experiment right here. I got a mirror right here, right? Okay. So what would a top to bottom reflection look like, do you think? We'd be upside down, right? We would reverse. Now, one way to sort of test that, right, is to take a pen, okay? And the reason I'm going to use a pen is because it has a tip, right? Okay? Can everybody see that my pen, it's a black pen, so it's going to be kind of hard to see, but this is the pointy end up here, and this is the flat end down here, which is the bottom, okay? And if I take my pen, try to get to a point where everybody can see it, and I hold my pen, right, in the mirror, okay? You can see the object here in the front, but in the mirror, which direction is the tip pointed compared to the actual object? Same direction. So is it flipping top to bottom? No. Okay? So it's not a top to bottom flip. Okay? All right. Let's do left to right. Okay? So if the mirror flips left to right, then what direction would we see the tip of the pen point? So I'm going to point the pen to the right. This is right for you, right? It's left for me. Okay, right? So if this mirror were to do a left to right flip, which way should the point of the pen be pointing in the mirror's reflection? Should be pointing to the left. You ready? Fake mirror? Tricky physics mirror? No, this is straight off Amazon, okay? Right? Okay, everybody knows everything on the internet's real, so if it's on Amazon, it's real, right? Okay, so this is not a right to left reflection, and I would bet that you walked in here thinking that mirrors flip left to right, and they don't. So if plane mirrors don't flip top to bottom, and they don't flip left to right, what's left? Front to back, right? Can you imagine what a front to back reflection might be?
I guess that. So if you look at it, you get to see the back.
Oh, so if you're looking in the mirror, you get to see the back of your head? No. That's what you do with two cell phones, right? Okay, or your computer and yourself, right? Okay, check the back of your head or whatever, right? You can't, no, okay? That's not a front to back reflection, and I'm about to show you a front to back reflection, okay? I'm going to hold the pen like this, okay? Tip towards the mirror. What end of the pencil do you see? You see the back of the pen, right? But what do you see in the mirror?
The front.
The front. That is a front to back reflection, okay? So now we need to figure out the government conspiracy why everybody thinks it's left to right, because it's not. Have you ever seen the word ambulance spelled on the front of an ambulance?
Yeah.
What does it look like? It's kind of weird. Look at it next time. Okay? On the very front hood of an ambulance, they spell the word ambulance funny. Okay? It's not spelled funny. The letters look funny.
So that when you look in the mirror,
So that when you're looking in your rearview mirror, it says ambulance.
Yeah.
Okay? But they haven't flipped it's not like it's backwards. Okay? But they've done a front to back reflection of some of the letters. Now, L and E fall victim to this, but A looks the same front to back. Okay? Look at it next time you see it. I should have a picture of it. I don't. So why do we think mirrors flip left to right? Well, it goes back to the question I primed your brain with, and I trapped you on purpose. Okay? By saying when you raise your right hand in the mirror, what do you see? You see your doppelganger raise their left hand, right? Why does that look like the left hand?
Because if you flipped it around, it would be your left.
Because human beings have a symmetry. Okay? There's a line of symmetry that runs down our bodies. Okay? Our internal organs do not represent, some do, but most don't. Okay? But externally, this symmetry is not a left-right symmetry. It's not a top-bottom symmetry. It's a front-to-back symmetry. the reflection of your right hand, front to back, is your left hand. Okay? So when the mirror flips front to back, you see a hand that looks like this, right? And so what does your brain do? It's got to be the left side, right? It's a lie. Okay? When you put your right hand up, it's your right hand that goes up, right? Okay? It's not like, so yeah, it's an optical illusion, right? And you were taught wrong by whichever person in authority you probably respect and love told you that it was a left to right flip. It's not. It's a front to back flip. And the problem is our hands are front to back images of each other. Okay? The human body symmetry is not perfect, and in fact, when it is, we get freaked out. Psychologists, brain function biologists have done these studies where they take a person's picture and they find the line of symmetry and then they perfectly flip it so that the left and right sides are just mirror images of each other. And people start freaking out when they see the pictures. Like they start feeling uncomfortable. Yeah. They start saying they're computer generated. It's called the uncanny valley. Humans have evolved very specialized ability to recognize faces. It's very important to our biology and our culture and societies and things like that. And when something is off, we can tell something's off even if we can't point it out. And oftentimes a person, one of your eyes is higher than the other, a little bit wider than the other. This is normal. This is beautiful. Okay, this is the way it's supposed to be. It's what our brains clue in on. When we see those asymmetries, we go, that's a person, right? But if you've got something like an AI avatar where they make everything look kind of perfect, we kind of go, that's not right. Okay, that's why a lot of more successful AI avatars are more cartoony, right? They give exaggerated expressions, and then it's in the realm of that's fake anyway, and our brains can work better with it. Okay, some other terminology that we're going to move using forward when we start getting into the harder mirrors. Okay, if you're standing, 50 centimeters, 1 meter in front of this mirror, how far away is your alter ego on the other side of the mirror? So 1 meter in front with the object, where's the image? 1 meter behind, right? Okay. Only there's a problem. There's nobody in there. Right? Like, right? Nothing back here, right? You're looking, hi. There's a whole mirror universe. There's a whole classroom inside of this thing, right? In my bathroom mirror, I come in the morning, I'm looking, right? There is not another Mr. Balogh standing on the other side of the wall because the other side of the wall is a 2-story drop to the backyard, right? So what the heck is going on? What are you looking at? You're looking at an image that's been formed in the mirror, an image that only exists in one place, in your brains. It's called a virtual image, and it is the true virtual reality. Because you can hold your hand up all day long. Toby, are there any hands on your side?
No.
Well, your hands, but not mine, right? Okay? So what we need to do is we need to start thinking and talking about how our physiology, how our brains and our Mark I eyeballs, how they, I specify now because we're getting close to being able to replace them. Okay? There are people who have lost their vision that have gotten it back. Yeah. Like we are living in Star Trek. It's absolutely incredible. Okay? But our minds and our brains are doing something. And I hope to try to explain this as I go along, and we'll get some formal terminology to be able to talk about what's going on here. Not all reflections are equal. This is just a slight tangent here. There are different sort of kinds of reflections. You have specular reflections like the one here on the left, and then you have this sort of spread out reflection on the right. The difference in these two reflections, the two beams of light, in this case laser, they're following the law of reflection. It's the law of the universe. You can't do anything about it. But do you notice how the surface is more rough on the one on the right? Okay. What practical effect does this have on our perception of what's going on? There's this phenomenon that happens elsewhere in the universe where actual water falls from the sky. I know it's hard for Fresnans to really understand what I'm talking about, right? Except maybe this winter. We've actually had a few storms, right? Okay. But when it rains, have you ever noticed that the lines on the road tend to disappear? Like at night when you're driving and you're seeing those reflections from the other lights, right? And you're driving along, all of a sudden you can't see the lane lines, right? This is the difference, right, between like a specular reflection where the reflection's coming off very intense and sort of overwhelms our eye's ability in contrast to be able to see what's going on, compared to this dry surface over here where it's still kind of difficult, but it is better, isn't it? Yeah. Right? So the kinds of reflection can make a difference in our perception of what's going on. I only mention that so that the next time you're driving in the rain, you'll be a little bit safer, realizing that you could be blinded or blind other people, right? Now, there's a safety feature. Has anybody noticed what it is so that you can actually see where the lane lines are, even if the surface of the road's covered with water? It's not the paint.
The pucks are
the little pucks, right? The little things that used to make fun of my friends for being braille drivers, right? Whenever they drive, oh, tunka, 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 tunka. Yeah, you're braille driving, dude, right? So those pucks are called retroreflectors. Not because they're cool and from the 80s or 90s, right? But because, what does retro mean? Straight back, okay? And so light goes into those pucks, and there's mirrors in there at special angles that guarantee no matter what direction the light comes in, the reflected light will come right back. It's a series of three mirrors that are put together in sort of a triangle pattern, and no matter how the light bounces, whatever angle it came in at is exactly the same angle that it comes out at. It's actually a pretty complex optical situation that they managed to engineer into something that is nearly indestructible, right? Like you can drive over it constantly and it'll keep working, right?
The fact is, if you look at, don't ever do this, but if you can see it in your rear view mirror, if you look in them in reverse, a lot of them they put red in.
So you know you're going the wrong way. Yeah. So red for don't go this way, right? White for it's okay. What's the other color that sometimes you see?
Yellow.
Blue, right? What's the blue for?
Fire hydrants.
Yeah, fire hydrants. Okay? There's a fire hydrant somewhere. Okay? If you see a blue one, just look left or right. There's a fire hydrant right there. Okay? It's so that the fire crews at night, as they're driving along, can see exactly where the fire hydrants are in the road. So what is our brain doing? Here is a mirror, okay? Important in optics is understanding where the observer is. So we often draw this disembodied creepy eye, okay, to sort of indicate what's going on there. Light is coming off of subject. We call the thing that the light's coming off of the object. Rays of light come off. Now, how many rays of light are coming off of this chess piece? Yeah, all of them is the answer, right? But in optics, we try to draw as few as possible so that we can be as clear as possible as to what's going on. So in this diagram, only one, because the one that leaves from the top and the one that leaves at the bottom are basically going to do the same thing, right? Okay? So light comes off of the object, strikes the mirror, obeys the law of reflection, and comes back to the eye. The eye sees that ray, but then what does your brain do? Your brain makes an assumption. What's the assumption? That light must travel in a straight line. because that's what light does, right? When there's no mirrors and the light just, right? Light doesn't go, right? It comes directly from whatever's causing it, right? It's called the principle of least distance. So your brain, having figured this out after eons of evolutionary practice, I mean, let's face it, you represent the successful organisms that all evaded the tigers in the grass, right? Your ancestors learned how to recognize when the grass wasn't grass anymore, right? And it was a tiger. And so using that evolutionary trick, right, your brain follows the light back to its source, creating a virtual image. The image of the chess piece on this screen. Everything you're seeing in this plane mirror right now is a virtual image constructed by your brain based on the assumption that light travels in straight lines. But is the light in a mirror traveling in a straight line? No, it's bouncing off, right? But your brain is going to fight for that information, right? And it's going to just make these assumptions, right? So we call this image that's being formed a virtual image. You can always tell when it's a virtual image because light rays, real rays, these are real rays that came off of this object, right? Real rays are being traced back, and then we use dotted lines for virtual rays, right? To follow the path that our eye is tracing back, and then our brain will form the virtual image that's right there. In a plane mirror, the object's height, its size, is exactly the same, whether it's the object or the image. In a plane mirror, the orientation of the object, we refer to this as upright. There's two kinds of orientation. You can have upright or inverted. We'll get to that in a second, okay? But this would be an upright, virtual, non-magnified image. Notice there were three things that I used to describe what's going on here, right? Is it real or is it virtual? What is its orientation? Upright or inverted? And then I use the word magnification, right? Is the thing that the virtual image you're seeing, is it bigger or smaller, right, than the object itself? In a plane mirror, it's 1-to-1, exactly the same, so we just say it's not magnified. We're going to use that terminology over and over and over again to describe images that are forming. So if there's virtual images, there must be real images, okay? And so we need to start talking about that, okay? Now, a plane mirror, a flat mirror, okay, is always going to be producing virtual images. You can't get around it, okay? But if we start changing the curvature of this mirror, we can start doing some pretty cool things, okay? So what we will do in Physics 2B is we will do spherical mirrors. Spherical mirrors are not, you don't make a big sphere, okay, and then cut mirrors out of it, okay? But in theory, that's what's happened. The curvatures of both of these mirrors come from a theoretical bigger sphere, right? It's as if we cut a section out of a big sphere that's shiny on the inside or the outside, depending on the curvature, right? And so it has what we call a spherical cross-section. In other words, the radius of curvature is equal in every direction. You can have you don't have to have spheres. You can do parabolas. You can do hyperbolas, okay? You can do any of the conic sections, right, for mirrors. We will not treat any of those. We are just going to do the spherical cross-sections, okay? So, how do we go about understanding what's going on here? Well, of course, this is physics. So we have theory, mathematical models that we can use to predict what's going on, and we also have experiment. If you were taking my class 20 years ago, we would have spent the next couple of days learning how to do ray traced diagrams. Okay? You live in an age where everybody now has a computer in the palm of their hands. Okay? And while I'm not going to let you use it on the exam, I'm also never going to ask you to draw a ray tracing diagram. But the ray tracing diagram is vitally important to understanding what's going on both in mirrors and in lenses. So I want to show you or share with you one of several resources that are available on the internet for getting a good handle on what's going on in optical systems. Okay? This happens to be my favorite because it's free and full-featured and was done by physicists, not artists. Okay? Artists have a tendency to mess things up. I mean, they try. They really try. Physicists, we can't make it look good, but it's going to be accurate, right? So I'm going to switch over to my other computer here, right? Does anybody recognize this? Unfortunately, yes. Okay, right? So course content. Down here in Unit 3, I've put the link, okay, to what I'm going to be using, okay? It's this optics simulation here. This is, it's supposed to be fully compliant to all the standards, so your phone should be able to do this, your iPads, everything. It's just running off HTML5. Let me know if it doesn't. Not that I can fix it, but if it's breaking on your phones or something like that, then maybe I need to find a different resource or something like that, okay? Notice you've got a choice between mirrors and lenses. We're doing mirrors today, so you can pick your mirror, okay? And then it's going to start running a simulation, okay? So this simulation is based on all the mathematics I'm going to teach you here in a little bit. But these are your visualizations, right? Remember in physics, you approach a problem by trying to visualize and organize your information. Then you strategize and you do it, then you check it. This is going to help with your visualization. There are some things I recommend that you do right off the bat. Okay, so there was an artist that got too much involved in this, so we're gonna fix this. Okay, right? First of all, you want to do the principal rays. This is what we teach in all the textbooks. There are other types of rays, okay, like marginal rays and things like that. Principal rays are the ones that are in your textbook and basically every textbook at this level. Marginal rays aren't used very often at all. Okay, so I would switch it to principal first. Okay, and then, sorry YouTubers, you're not going to be able to see any of this. I would change your object to an arrow. Okay, you can of course choose a penguin if you want to. Okay, but arrows are the standard. Okay, and they will help you see what's going on in any given situation. Okay, if you're sitting there despairing right now, oh my gosh, there's no way I'm going to get any of this on a cheat sheet. I'm dead. Don't worry, I got you back. Okay, we'll figure that out later. Okay, but let's just get into what's going on here. You can take and grab the object and move it around. You see that? Okay, you can make it taller. You can do all kinds of stuff with it. Try to make it so that it's hitting your mirror. This is still working. The simulation is still functioning correctly, right? It's just that this makes more sense, right? When all the rays are hitting your mirror, okay? You can change the diameter of your mirror just to make it look bigger, right? So it looks better. Don't mess with the radius or curvature. And you can put the labels on if you want, okay? I'm going to leave them off, but my other pictures will have them on, okay? So as you can see here, I can move my objects in and out, right? Do you see this yellow dot right here? That's the focal point, okay? The focal point of a mirror is the place, right? If I move this thing kind of far away, do you see how some of the rays are trying to get to the focal point? By definition, if all the rays are moving parallel to that dotted line, the optical axis, all rays will come in, bounce off the mirror, and pass through that focal point. We'll talk more about what far away means later, okay? But I want you to notice something, okay? First of all, this mirror is what we call concave. The shiny side is always on the side that has the object. And if you had to tell me what kind of image is being formed, okay? Remember, there's three ways to talk about the qualities of the image, right? We've got real or virtual, we've got magnified or reduced, and then we've got upright or inverted. It doesn't really matter what order you do it in, okay? So let's tackle upright or inverted. Inverted, how do you know? The arrow is down. For those of you that are wondering, the penguin is down, okay? But again, it's just not as clear as having an arrow, right? Okay, so this is an inverted image, okay? Magnified or reduced? Can you see how that image is smaller than the original object? Okay. Is it real or is it virtual? This is a real image. Do you see how the real rays have come together to form? All three rays have left the tip of that arrow, bounced off the mirror, and then come back together at the tip of the image. That's how we know where the image is. It's when those three rays come together. But this is a real image. If I take this, oh, that's interesting. What happened? Is it real or virtual? Still real. There's still three real rays coming together to form that image. Magnified or reduced? Magnified now. Upright or inverted? Inverted. Okay. Watch what happens when I come to this side. Upright or inverted? Magnified or reduced? Real or virtual? How do you know it's virtual this time? The front side of the mirror is where the eyeballs would be. We don't have an eyeball on this diagram, okay? So your eyes are going to see these three rays on this side of the mirror that are diverging from each other. So if light's coming at you and it looks like it's diverging, what's your brain going to do?
Finish them.
Follow them back to the point of convergence, forming a virtual image in the mirror. The reason I show you this, so I'm going to switch away from this now. We'll come back to it when we do the other mirror. But this is for you to mess around with, to get an idea of like what happens, right? What made the change? Like what happened? Where is the object in relation to the focal point for this virtual image to form? It's inside, right? It's closer to the mirror than the focal point. But as soon as we get outside of the focal point, it's not on the back side of the mirror anymore, right? So I encourage you to go in here and just sort of mess around, right? See what happens when you put things in different places and all that kind of stuff. And you'll end up with an understanding that there are some simple rules that are governing what's going on here. So the radius of curvature just basically adjusts where the focal point is, okay? You really don't have to mess with it. You can if you want, okay? You can always reset everything by hitting this counterclockwise direction indicator button, okay? And then it'll reset back to its things, and then you'll have to go back to arrow. You'll have to go back to principal, right? Diameter, whatever. Yeah.
Will you change it to a pencil and then move the pencil to the right side of the focal point?
Okay, so. Yeah, I don't know why you're doing pencil, because penguin is the answer. Yeah. Okay? But the problem with all of these other things is they don't let you adjust the height. Right? And so usually what I do is I lock so that the height can't change. And now I can just drag along the optical axis. Because that's actually where all the interesting things are happening anyway. Okay? All right. Back to plain pieces of electronic paper. Yeah?
So what does a real reflection look like?
Don't worry, I've got your back. I got your back, okay? Taking baby steps here, right? Because I'm laying a foundation for all the terminology that we are going to be using like for the next 2.5 weeks, right? Like, you're going to be sick of uprighted, inverted, magnified and reduced, real or virtual. I don't know anymore, right? But how is this compared to magnetic fields and right-hand rules? This is better, right? Okay, like hands down, this is way better, right? Okay, so what have I done here? I'll include this in the PDF. I took screenshots, right, of that program that I really strongly encourage you to go in and play with so you get a feel for what's going on, right? But there are basically 3, look at the top one, don't look at the bottom one yet. Because we haven't talked about this kind of mirror yet, right? Okay. I put them all on one page for ease of reference, okay? But the top 2 are concave mirrors, right? It's labeled down here, convex. We'll do that one later, okay? But basically there were 2 regimes, weren't there? There was that when the object was outside the focal point, I got this kind of image, didn't I? Notice magnified or reduced depended on where it was, right? So you really can't assume that it's always going to be reduced. I showed you that in the simulation, right? When I draw that, remember I drew it closer and it got bigger, but it was still real. So you got to be careful there, right? But the 2 main sort of regimes were object outside the focal length producing a real image and an object inside the focal point producing a virtual image, right? Those are kind of the 2 big categories of what's going on when it comes to concave mirrors. Okay, so what does this look like? And then we will do some math to line it all up, okay? So this is a concave mirror. The way that I choose to remember that this is, because concave and convex, they're just words, they don't mean much to me, right? You're trying to walk into a cave. The object is, right, the cave opening, right, is looming over. You walk into that's how I remember it, right? And then convex is the one that's not a cave. That's how I do that, right? Okay. So it's the shiny side is kind of curving towards the objects. You guys are the objects, okay? And so I'm going to hold this up, right? What do you see? Is it inverted? It's inverted, isn't it? Okay. And is it magnified or reduced? Reduced? Kind of? People that are closer might start arguing with you. Okay. Is it real or is it virtual? Which picture are we? The left or right top picture? We're on the left. Do you see how you're seeing an upside down thing? Okay. This is something not everybody can experience right now, but I'll send you home and help you experience it with something you probably have at home already, okay? But I'm going to torture the front row people with this, okay? I just want the rest of you, I want you to watch their reactions, okay? Right? Oh gosh, okay. Oh goodness. Yeah?
Oh shit.
Watch your language. Oh yeah, it was really cool. Okay. What did you guys see, front rowers? Huge. A huge version of yourself, right? Okay. Magnified or reduced? Magnified. Like what they saw was their face like 3 times bigger than it should be. Okay. And it was kind of scary, wasn't it? Okay. Because what did your brains do?
Freak out.
Yeah, they went, faces aren't that big. Ah! Right? This is what happened, okay? So they saw a magnified, upright or inverted? Upright. It was upright. Everything was right, okay? Right?
That was weird. I could still see inverted behind my face.
Magnified, upright, real or virtual?
Real.
Virtual. Because what I did is I stuck your face inside the focal length of this mirror. Okay? Everybody else was outside, so they saw inverted, all that kind of stuff, right? But when you get up close. Okay, yeah.
So like, if you hold it up, so like the whole class is inverted, but then you have your hand closed, is it possible to see an inverted image of us and then an upright?
Yeah. So I took the pictures out. I should have kept them in. I'm going to get sexist for just a second. Okay, I know. It's terrible of me, right? Okay. Ladies, what is this? Have you used one of these this morning?
It's in my pocket.
Yeah, it's a compact mirror. Okay? When you open the compact, right, and you can see detailed up close things, right? Okay? Gentlemen, what is this? It's not used very often anymore.
It's a grocery store.
No. Good guess.
The shaving mirror?
Shaving mirrors. So nowadays I think they're just called makeup mirrors. You have like a bigger version than your compact, but it's on like a stand. So there's a compact, right? Okay.
Thank you very much.
Yes, no, that's why I was being sexist, right? Okay. This is California. We can do whatever we want, right? Okay. So the idea of the makeup mirror or the compact or the shaving mirror, right, is to do what? Really get in there. Be able to pull those nose hairs out really well, right? Okay. TMI. So if you've got like a makeup mirror or a compact or a shaving mirror, right, at home, you can see what's going on here, right? If you remind me on Monday, I'll bring these into lab and you can see it, right? You just probably have to just, hey, Mr. Bailey, go get the mirrors. I'll be okay. Look at the mirrors, okay? So let's talk about how we are going to deal with calculating what's going on, modeling what's going on, problem solving with what's going on. I'm going to hand out something. Everybody needs one of these, okay? Yeah, this is important, okay? It's so important that I actually put it, so this is called paper.
It's what your exams are made out of.
Right? Okay. The reason I printed it out was to reinforce the idea of just how important what we're going to talk about is. This piece of paper, go ahead and take a picture of it, put it in your phone, whatever, but you're going to want to have this on your cheat sheet. Okay? Reproduce it on your cheat sheet. I could, PJ, did you give it? Yeah. So you can glue this to your cheat sheet. I should probably provide it for you on the exam, but I don't because I'm stupid and I can never remember. So just redo it, put it on your cheat sheet, whatever. Did we get enough? We got enough? Okay. This is your, two more? This is your coordinate system, right? In 2A, we were always about like what direction's X, what direction's Y, all that kind of stuff. And this is it for optics, okay? These are the rules and conventions that we all abide by so that we can be talking about the same thing. The front side of a mirror is the shiny side. It doesn't matter if it's curved or flat. The front side is the reflective side, okay? So in all of the diagrams I have on the screen right here, the front side is on the left. But I could have just as easily put the object over here and made this the shiny side, which would mean the right side would be this front side. So the front side, by definition, is whatever side the shiny side of the mirror is, and for you guys, will always be the side that the object is on. There are cases where you can put the object on the back side, but it's a multiple optic system. We're not going to go there, okay? So that's what we mean by front, okay? So what's the back side of a mirror? The not shiny side, right? The non-reflective side, okay? What I've done over here, these are the three things that we're going to be using, and I'm going to put it on this screen just so we have it all in one spot. The mirror equation is this. It's a relationship between the distance to the object, the distance to the image, and the focal length of the mirror. There's other relationships here. Magnification is minus image distance divided by object distance, by definition. We'll get to that in a second. There's an alternative to this. You can also do height of image over height of object. Here, the plus or minus sign is a little bit less concrete, okay? But it is the same thing. And then just 4 mirrors in specifically. The focal length is always for a spherical mirror, the focal length is the radius of curvature divided by 2. What the heck is the radius of curvature? Remember, we're sort of taking this mirror out of a sphere of glass. Again, we don't really do it that way, but like that's the idea. The focal length will always be halfway. So if this whole distance, capital R, is the radius of curvature of the original sphere, then the focal length will be half the radius of that thing. Sometimes it's depicted in diagrams as the center of curvature, C, big capital C.
So, Mr. Balogh, would little compact mirrors for, make up this up, would they have a smaller f
Yeah, do they have a smaller radius of curvature? Yeah.
versus those ones?
Yep, these are pretty big, okay? But the ones in the boxes are the main ones. This one over here, I'm going to put it in a box anyway. I don't know that your book gives it, but it comes in handy for like when they ask you, like a 10 centimeter high object, how big is it in the mirror, right? You can calculate how big it's going to be. Notice over here in the table, I have done something kind of weird. DO and DI is what I use internally all the time when I am doing optics. P and Q were what I was taught. Have you ever heard the phrase, mind your P's and Q's? Okay. Historically, object distance was represented by P, and image distance was represented by Q. What do you think that does to a dyslexic person's brain?
Terrible thing.
Because a P and a Q are the same letter.
Yeah.
Okay? So I always went with DODI internally. With the subscripts to me have always seemed, I don't flip subscripts, right? So DO meaning distance to object, DI meaning distance to image, okay? It's what your book uses. It's a modern, I see it coming into more and more use nowadays, okay? The other one that sometimes crops up, and this is not standard, but I've seen it on the internet, is I for image distance. They don't seem to use O for object distance, but some reason all of a sudden you've got a little I somewhere, and you're like, what's the square root of -1 doing here, right? DIDO, let's stick with that, okay? F for focal length, okay? If we come over here, right, the focal length of this mirror, what side of the mirror is it on? Front or back? Front. So what sign do we use for that focal length? Positive, right? Over here, what side?
In front.
In front, so positive focal length, right? Spoiler alert, when we get to the convex mirror, what side is the focal length on? The back. This is the shiny side because this is the side where the object is, right? Focal length's here on the back. So for a convex mirror, we would use a negative focal length. You are going to live and die on this table. Seriously, when you email me about how Wiley Plus hates you and it's not giving you the right answer and you know you're doing it right, and here's my work, Mr. Balogh, I'm going to send it back with a single sign circled. And you're going to die inside. Okay? You're just going to die because you just spent 3 hours arguing with the computer and all you forgot to do was put a minus sign on a focal length. Obey this. Like seriously, obey this. This is where you will lose points on the exam. It's here, okay? Because the rest of it isn't hard, okay? But keeping track of things can be very difficult. So let's do an example of working with a mirror that is concave. Where did I put my examples? Right somewhere. Okay, let's do, and I just made up numbers for my notes. These numbers were made up because I used to have to draw all the ray tracing diagrams on the board, right? And I needed everybody to be able to see what was going on, but I don't have to do that anymore. So I should probably update my numbers. But let's just say that this is a concave mirror, okay? You're given a focal length, and they do this a lot. They'll say a convex mirror of focal length 15 centimeters. What do you have to do? Notice I said convex. If it's convex, what's the focal length? Negative. They won't put negative on it sometimes. They'll just say convex and then give you a number. Again, they're trying to trick you, right? So I fall guilty to this sometimes because I just see convex and I know it's negative, right? Concave, I know it's positive, right? But if this is a concave mirror, right, then the focal length has to be what? Well, how do I know, Mr. Balogh? Because you're going to draw a little sketch, or you're going to look at a little sketch and go, okay, I have an object, right? I know it's a concave mirror, so my object is somewhere on the front side, right? This is the front, this is the back, right? And my focal, I don't know where my focal length is yet, right? Or where my object is in terms of my focal length, but this focal length has to be positive 15. Like, I can't emphasize enough how important this sign is, because it's going to determine your answer, okay? And the math isn't going to be hard. Okay, so focal length of 15. The object's height is 10 centimeters. I may not use that. And the distance that that object is 40 centimeters. Okay, so how are we going to do our little sketch here? Where do I put, so I forgot to tell you something. There's always this optical axis, right? This line that it meets in the middle of the mirror, okay? Objects, images, they all are referenced from the optical axis. The distance is measured from a point called the vertex. It's where the mirror crosses the optical axis. That's your reference point for everything. So 40 centimeters from that, this is your object distance. Not to scale, but just in sketching, where do I put the focal point? If that distance right there is about 40 centimeters, where am I going to put the focal point? Am I going to put it here, here, or here? The second option, right? It's a number that is less than my object distance. So again, it's like my visualization, right? I'm trying to get what the problem's telling me. I'm going to get it down in a picture. Okay? Once you have this orientation and this little sketch down, you can actually start predicting what's going to happen. If you go back to here, which of these pictures now do we have? Top left. The object is outside the focal length. The focal length is between the object and the mirror, right? So we know it's going to be something like this. So what do we already know? Is it real or is it virtual? It's going to be real. Okay? Is it upright or inverted? Yeah, I took the picture away from you. Right? Because it's this situation, I'm going, okay, it's real and it's inverted, right? Okay? Magnified or reduced? Not sure. We can calculate that. It looked reduced, but like I said, if we get too close to the focal length, it can start getting magnified, right? So we'll kind of leave that one for now, okay? But this is like a guess or based on the picture, right? This is what we expect to have happen, right? Okay? So let's see what happens. We're going to calculate the image distance. We know the focal length, we know the object distance, so we're going to go and we're going to find the image distance. I solved this equation for di, which is 1 over f minus 1 over do, but I do have to remember to invert my answer when I'm done, right? I did quite a bit of algebra there. This is not a math class, okay? So now I've got to make sure I get everything in here correctly. The focal length, I rammed that home, that has to be positive. Object distance, positive or negative? Object distance is positive if the object's on the front of the lens. Is it ever on the back of the lens for you guys? No, so always going to be positive. But we're gonna make sure that we put a positive sign on there to remind us that we did think about it. Okay, so this is 1 over positive 15. I would put the signs in everywhere, like seriously. Okay, what?
Centimeters.
Yeah, it's okay. If I put this all in, okay, that's another good point. Sorry, I I got all optical physics on you. We usually do things in centimeters in optics. Okay? It doesn't matter if it's centimeters or meters, as long as everything's the same. So if you work all in centimeters, what's your answer going to come out in? Centimeters. Okay? What, again, this is something they'll try to trick you with. They'll tell you the focal length is 15 centimeters and the object is 1.2 meters away. What do you have to do? Pick one and convert. Okay? Get them all in centimeters or get them all in meters. Right? But just make sure everything has the same length unit. Okay? So, yeah, centimeters is fine. So 1 over positive 15 minus a 1 over positive 40. Really, just emphasize those signs. Otherwise, you're just going to be chasing math problems so much. It's just going to be so bad. I got 24 centimeters. Positive 24 centimeters. Okay? What does positive mean? The image distance being positive means what? It's in front of the mirror. Is that what our picture predicts?
Yes.
Yes. So we're doing okay, right? Magnification. Negative image distance divided by object distance. That's a minus a positive 24 divided by 40. And I got 0.6, negative 0.6. Okay? So, what does the negative sign on the magnification mean? It's inverted. And is it inverted in our picture? Sure is. Okay? Magnification has no units. I divided a centimeter by a centimeter. So, what are the units? No units, right? Because it's a number that's less than 1, it means that it's reduced. So magnifications less than 1 are reduced. Magnifications bigger than 1 are magnified. So if your magnification was 2, then the image is now twice as big as the object, right? This one is roughly 60% the size, reduced. Okay, so now I can actually find the height of my image, what is the actual, if the object was 10 centimeters high, right? What I do is I take the magnification and multiply it by the object height. 0.6 times 10 gives me 6 centimeters, right? So it's reduced, and since I knew the object was 10 centimeters tall, I can find out how big the image is going to be, wherever it is. Okay, so that was concave mirror, right, with the object outside the focal length. So let's do another one where this time we put the object inside the focal length. So I'm going to say the focal length is plus 15. If I say the focal length is plus 15, I've given you the sign. What do you now know about the mirror? Has to be concave. How do you know that? I meant to circle front at the top. Front, focal length is on the front. If it's positive focal length, then it has to be on the front. If it's on the front, it's got to be one of these two, right? Okay. All right. So, that being the case, we know it's a concave mirror. Let's set the object distance. What did I put down? I put down 10 centimeters. Okay. We are now in this picture, aren't we? Focal length is bigger than, so object distance coming from the vertex, that's smaller than the focal length is. Little tiny sketch of the situation always helps. You'll have words. I'm not giving you words right now. So there's the focal length. My object is somewhere in here, right? It's inside, right? So based on that, we know that we need to get what kind of image? Virtual, magnified, upright. So there's no way in the mathematics to tell real from virtual. The only way to tell real from virtual is if real rays converge. If real rays converge, then you will be having a real image. The screen you're looking at right now is a real image. How do I know it's a real image? Real rays are present. Do you see how my hand can block the light coming from the projector? That's a real image because I'm interfering with the real rays that are present. A virtual image? Am I interfering with what you are seeing? No. Doesn't matter what's going on back here, right? Okay. 1 over f equals 1 over do plus 1 over di, which when you do this gets you di equals 1 over f minus 1 over do. Don't forget to invert the whole thing. 1 over 15, positive 15, minus 1 over positive 10, inverted, gets me negative 30 centimeters. Okay, that's my image distance. What's the negative sign mean? An image distance that is negative will be on the back side. Is that what we expected to have happen? You betcha. Okay, so that seems consistent. What's the magnification going to be? Minus di over do. So that's a minus 30 all over 10, which is a positive 3. So if this object were 10 centimeters high, how big is it in the mirror? 30. Right? It's 3 times as big. Okay? There's the magnification. Real or virtual, we checked with the diagram. Magnified, it definitely is, and it's upright because it had a positive magnification. You can check yourself 6 ways from Tuesday in optics. There really should be no wondering what's going on, right? You have the picture, you have the math, and if the two are not agreeing, there's a problem, fix it, right? The problem could be in your understanding, but really they should all be agreeing with each other. This is an example of a concave mirror. This mirror is not optical wavelengths. This is radio wavelengths, but this is how satellite TV works. Okay. Where are the sensors? They're at the focal point of the mirror. Okay. All right, let's do a convex mirror. Convex, what do we know about convex mirrors? Look at your sign conventions. You tell me the focal length has to be what? It has to be negative. I'll keep using 15. Okay. So we know the focal length is negative 15. Our picture, way back here, I'm only going to show it to you once, is this one down here, right? Okay. So when we draw our little sketch, and I would recommend that you do this, right? Draw a little sketch and then compare it with the actual diagram, right? See how I made it curve away from the object? Here's my object, right? And where's the focal length, front or back side? It's on the back side, over here, right? All right. So that focal length 15 doesn't really matter what the object distance is since you only get one solution for this. So I'm just going to go straight to di equals 1 over f minus 1 over do to the negative 1. 1 over positive 15? No. What am I going to put in? Negative 15. It's those signs that are going to kill you. Minus 1 over, what did I do for the object distance? 20 centimeters. Remember, this is the front, this is the front side because this is the shiny side, right? The side with the object on it. This is the back side. And object distance is always positive on the front side. Negative 1. When I did that, I got negative 8.57 centimeters. Where is this image located? If I have a negative sign on this, where is it located?
On the back side.
According to the sign conventions, it's on the back side.
Front of the focal.
Okay, meaning it's a virtual image, right? Let's calculate the magnification. Negative image over object distance, negative and negative 8.57 divided by 20. I can already tell this is going to be reduced, but it is a positive 0.4285. Positive, meaning upright. Okay, so we know it's virtual. We know it's upright, and 0.4285 means reduced. That's this mirror right here. Okay, Alex, where have you seen these? The grocery store, okay? Or the clothing store, actually any store that really has security cameras in it, okay? Because what is this mirror doing? If I come over here, we'll go to the door, okay? You see them in hospitals, okay? What is this mirror doing? What can you now see? You can see around the corner, right? This mirror has widened the field of view that you can see. You put a plain mirror in the corner and you can't get a wide field of view. This widens the field of view, but do you see how everything looks smaller? Okay, so this is a bit of a lie, because what kind of image is it? It's a virtual image, so where's it forming? In your brain. Objects in mirror are closer than they appear. You get a wider field of view, but you lose depth perception. These mirrors are put on the passenger side of vehicles so that you can do what? See into the blind spot, right? Okay. But officer, I swear that car was further away from me while I was backing up. Speeds of things in these mirrors are not consistent and not linear. The closer something gets, the faster it will move. The further away it is, the slower it will appear to move. Okay? You can't judge depth looking into that mirror. Why are rear view mirrors always plane mirrors? Because you need the accurate distance, okay? Unless you've got a car where you can't see out the back anyway, in which case, have a backup camera. I will leave you with this thought. I'll see you on Monday.
What is that?
It's a big eyeball.